All right. Hello, everyone. Thank you for joining us tonight for our event, Anti-Aging with Jack Harley. I'm Alistair, and I'll be hosting this event with Max, the events director of EA Unimelb. Before we begin, I would like to acknowledge the Wurundjeri people, who are the traditional custodians of this land. We'd also like to pay respect to elders both past, present, and emerging of the Kulin Nation. I also extend that respect to other Indigenous Australians present. Before I introduce our guest, Jack, I'd also like to invite you to join Effective Altruism Unimelb, or EA Unimelb, using the membership sign-up link we've put in the chat. Feel free to also like and follow our Facebook page. If you weren't already aware, Effective Altruism is a movement that seeks to answer the question of how we can do the most good with our limited resources. We run in-depth discussion events, career workshops, and guest speaker discussions like these, along with a whole range of social events. Even during COVID, EA Unimelb in particular is known for its warm and inviting community. So if you're looking for some new friends who are interested in making the world a better place, we'd love to see you at our next catch-up. Now, with us tonight, we're very, very fortunate to have Jack Harley, an effective altruist and researcher in the anti-aging space. Jack is a guest lecturer in clinical neuroscience at the University of Oxford, and also the founder of the Longevity Wiki, the world's first open longevity education program. Before I hand it over to Jack, if you have any questions at all throughout the presentation, just send them through the chat box, or if you would prefer, we also have the Google form. We will answer them at the end. Take it away, Jack.
Great, thanks for that introduction, Alistair. So I'll just pull up my slides here and hopefully we can all see. So can everyone see my screen here?
Yeah, all good.
Cool. All right, so this is going to be quite an introductory talk. Anti-aging and EA is a big topic, but I'll just spend about 30 minutes or so introducing the principles of anti-aging and describing how it links to EA. And I'm going to assume, not too much knowledge in this topic, so I'll just go through it nice and steadily and easily, so you can hopefully follow along. And here's a quote from Elon Musk from last year: "With effort that's not too crazy, you could probably stop aging or reverse it." Now that might be quite a speculative kind of claim, but hopefully after today's presentation, it might be less crazy than it seems. So a bit about me. I'm here because I'm interested in anti-aging science and its relevance to EA. Here are some of my affiliations. Recently studied at Oxford and did some lecturing there. I work for a US biotech company, which is called Revivo Therapeutics, which is in the neurospace, developing Alzheimer's therapeutics. And here are some of my other affiliations. So the two kind of theses of this talk are, firstly, that medical research into the biology of aging, which is known as geroscience, is potentially a very important and neglected cause area, and hence one that EA should take note of. And secondly, that donations to fund such research are potentially more cost effective at saving human life years, or QALYs, which are quality adjusted life years, than GiveWell's current top charities. Okay, so basically this presentation is about, should we give money to anti-aging research or geroscience research over other cause areas? And of course, with EA, it's all about doing the most good that you can. So with limited resources, how can you bring about the most good? And I'm going to make the case that geroscience funding and funding the medical research in this area is potentially one of the most high impact areas. All right, so let's start off with the basics. So what is aging and why should we try and cure aging? And again, this may seem like quite a jarring statement because aging is so entrenched into our whole culture, our whole society, but we have to try and put aside some of our preconceived notions about the fatalism and the inevitability of aging and approach this with an open mind. And we may see that aging is not as great as we think it is, and something that we may be able to do something about. So aging is basically this biological process that takes the organism, a human being, for example, from being young and fit and youthful to being kind of decrepit and old. And obviously, even the royals succumb to the ravages of aging, sadly. And it's the leading risk factor for cancer, Alzheimer's, diabetes, and heart disease. In Australia and developed nations, 90% of people die of aging. They may differ in terms of which disease they die of. It might be cancer, heart disease, and so on. But in developed nations, 90% of people dying, and worldwide, 70% of people are dying due to aging. And this equates to about 150,000 deaths per day, or somewhere in the realm of 36 million per year. So when we talk about aging, it's important that we distinguish between biological aging and chronological aging. So when I ask how old are you, if you say you're 20 or 25 or 30, you're talking about your calendar age, which is your chronological age, simply the number of years since your birth. But when we talk about age in geroscience, often we're talking about your biological age, which is actually a more accurate measurement of your physiological age. It's also known as phenotypic age, and it takes into account the gradual accumulation of damage to the cells and tissues across your lifespan. So this is influenced by genetics, diet, lifestyle, and even recently, it's been shown to be influenced by certain anti-aging interventions. So to give you an example, there's literature showing that if you smoke, it accelerates your biological age, which can be measured using these aging clocks, which I can go more into if you're interested. But for instance, you can look inside the cells at the DNA, and in particular the methylation, which is like these sort of tags on the DNA, which is part of your epigenome, epigenetics. You can look at the epigenome, and using these machine learning technologies, which is known as the Horvath's clock, you can actually identify how old someone is biologically. So someone may be 20 years old in terms of their chronological age, but maybe they've smoked there for 5 or 10 years, and they have an accelerated biological age, or vice versa. Okay, so when we talk about anti-aging, we're not talking about changing your calendar age. Obviously, the arrow of time is sort of this inevitable, physical sort of process. We're talking about altering your biological age. So you may be, 40 years old chronologically, but you may have a biological age of 30 or 20 using this new technology. So just to give an example, David Sinclair, who's a professor at Harvard Medical School and sort of an aging biology researcher, author of this New York Times bestseller called Lifespan: Why We Age and Why We Don't Have to. So his chronological age is 53, and he looks pretty good for his age. And in fact, he's taken these biological age tests, and his biological age is 31.4. So basically, that means physically he is as healthy and as kind of vital as a 31-year-old, despite having lived on the earth for 53 years. And this is measured based on these blood-based aging clocks, as well as the epigenetic aging clock tests that I alluded to before. And here's just an illustration of those. So again, when we think about anti-aging, we're thinking about a decoupling between your chronological age and your biological age, which is, how is your organism doing? Are you young, fit, and healthy, or is your body, aging and decrepit? So just to go back to why aging is a problem, this is just an illustration proportionally illustrating, the major causes of death in the world. Terrorism and war, they get a lot of media attention, but in terms of the number of people who at this point in time are actually dying, it's very small. And lo and behold, the major source of death worldwide are these age-related diseases. So the biggest one is basically heart diseases, such as heart attacks and so on. And then cancer is the second one. And then we have respiratory disorders, nervous system disorders, which include Alzheimer's, Parkinson's disease, other neurodegenerative conditions, and so on. So as I alluded to before, aging is the leading cause of death amongst humans worldwide, responsible for 70% of deaths. And interestingly, some people have created these mathematical models to estimate what the human lifespan would be on average without aging. And they suggest that it would be around 1,000 years, taking a conservative estimate. So because we, as humans, we have this degeneration in our body that eventually kills us, that's why our lifespans are so much shorter than they otherwise would be. If we didn't have this aging process, we would live to on average 1,000. Obviously, we can die of accidents, natural disasters, violence, etc. But if we removed aging from the equation, our lifespan would be much longer. This is healthy lifespan. So the reason why aging is so effective at basically causing mortality is because of the exponentially increasing risk of age-related diseases associated with the aging process. So as you can see from this graph, until you're about 30, your risk of dying of these sort of non-communicable diseases, these age-related conditions, is quite low. But once you start hitting 45, 50, 60, 70, and so on, you have this exponentially increasing risk of these diseases. So cancer in red is illustrated here, heart disease in green, type 2 diabetes here in blue, and so on. And I think this graph is so important that people understand, because when we think about cancer, I think a lot of people don't realize like how strongly correlated with age it is. Now, obviously, there are these sort of congenital forms of cancer that can afflict young people. So young people can get cancer, but this is a very minuscule percentage compared to the overwhelming majority of cancer incidence. Okay, so this is a really important graph to understand, because this is why we need to treat aging, because it's basically our body's degenerating, and it's part of the etiology of these diseases such as cancer. And I don't want this to be a sort of biology class, but later on, if you're interested, I can go into more about the sort of the pathogenesis of some of these age-related diseases and how they link to the fundamental sort of processes of aging. So because of this, this is why we have this Gompertz-Mackenham law of mortality, which basically means after the age of 30, your risk of dying doubles every 8 years. Okay, so it's not the most sort of enticing graph. It's a little bit scary to think about, but this is a logarithmic sort of scale. And as you can see, your risk of dying per year is fairly low if you're under 30. But as you can see, it kind of gets worse and worse until when you get to the 90s, it becomes something like 1 in 5. So if a 90-year-old has something like a 1 in 5 chance of dying any particular year. Okay, and again, this is due to this aging process, which is linked with all these age-related conditions. But the thing about aging is it's not just the death that it causes that means that it's a potential target for EAs and as an EA cause area. It also causes an enormous amount of suffering. Okay, just think about the kind of the DALYs, the disability adjusted life years, associated with all of those conditions that I've mentioned, as well as all the other age-related changes. As you become older, you become more frail. There's even higher incidence of several psychiatric conditions, which I can show you some slides about if you're interested. But basically, everything's going wrong with your body, and it causes huge amounts of disability. Okay, and this is something that, as a society, we don't always like to focus on, because it's a bit scary for us to consider that this is, the path that we're all destined for, unless we can, really work on these anti-aging therapeutics. But basically, 30% of all disability-adjusted life years, are associated with the aging process. And so there's an immense amount of value to be captured if we can start kind of targeting this aging process and extending the healthy period of lifespan before those age-related processes of decline really take hold. But even just to expand upon the amount of value that's at stake, the healthcare system is absolutely immensely burdened by age-related decline. This is worldwide. Okay, so to give you an idea, so the US, about almost 20% of its GDP is spent on healthcare, and as you can see, these age-related diseases are immense expenses. I think even nowadays, this is from a couple of years ago, but these are almost all at $1 trillion. So, dealing with dementias is about $1 trillion. Cardiovascular disease, another $1 trillion. Cancer, $1 trillion. So there's immense amount of financing required to basically deal with these age-related diseases that are linked to this underlying biological process of aging. So let's just zoom out a bit and let's just talk about what is aging, okay? Because I've talked about how this process that occurs across the lifespan leads to these diseases, but what are those processes? So this, as I said, it's not going to be a biology lesson, but one key reference that I want to point you towards if you are interested in this, and maybe if you have sort of a biomedical background, is this paper called The Hallmarks of Aging from 2013, which is kind of like the prevailing paradigm in the aging field for how we think about aging, okay? So basically, there are 9 general kind of categories for the types of damage that we accumulate, over time that lead to these pathologies. And I'm sure some of them, you may have heard of, such as telomere attrition. So the telomeres, these caps on the end of your chromosomes, they shorten over time. That's one of the changes. But there's also these other changes. So you have DNA damage. So even if you get severe sunburn, it's kind of causing an accelerated rate of DNA damage. If you smoke heavily, that contributes to this genomic instability. But you also have all these other changes, such as loss of proteostasis, which means the balance of your proteins within your cells and tissues, becomes skewed and becomes dysregulated. You have epigenetic changes, so the tags on your DNA, the methyl tags and their pattern kind of changes. You have cellular senescence, which means you have these kind of death-resistant zombified cells that release these pro-inflammatory cytokines and pro-inflammatory factors, which has led to this term inflammaging, which means this increased inflammation, this chronic low-grade inflammation that many elderly people have, and so on. So you have these changes, and these are basically the root causes of all of the kind of physical changes that you see. So the gray hair, the wrinkles, the increased predisposition for diabetes, cancer, and so on. It kind of all links back to these basic changes in your biochemistry and your cell biology. And this original paper has been really set the frame of the debate for a lot of this field in the last 8 years, and so it has over 8,000 academic citations. So it's a very frequently referenced paper, and it's a really good overview for those who are interested. Now, how does this relate to EA? Well, many of you will be familiar with Nick Bostrom, who was, who still is a professor at Oxford. And he's most well known for his books in the EA circles of superintelligence and writing about the dangers of artificial intelligence. But he has also written about aging and tried to convince people that it is an important cause area. If you're interested, he's got this great little fable. It's called The Fable of the Dragon Tyrant. It's basically a short essay in which he creates this narrative of this dragon that's killing the population, and the population are quite, complacent about it. And they're so kind of conditioned into thinking that it's normal that they never consider that it's actually problematic. And here's just a quote from that essay after he's given the story. There's a bit of explanation, and he says, "The ethical argument that the fable presents is simple. There are obvious and compelling moral reasons for the people in the fable to get rid of the dragon." Again, the dragon is kind of a metaphor for aging. "Our situation with regard to human senescence is closely analogous and ethically isomorphic to the situation of the people in the fable with regard to the dragon. Therefore, we have compelling moral reasons to get rid of human senescence." So basically, he's saying that, if we think about things logically, if we think about the ethics involved of aging, whether we should have this kind of complacent attitude towards it and just say, oh, it's natural, etc., or whether we should say, no, it's actually killing a lot of people, it's causing a lot of suffering, we should treat it. He's arguing sort of the latter. But he's not the only EA to talk about this. So this is Anders Sandberg, who's also well known in the EA circles. And on the 80,000 Hours podcast, he's given this quote. He said, "But given that 100,000 people die each day of age-related conditions, that seems to suggest that actually quite a lot of value is at stake. So the scope of aging as a threat is tremendously important. It's also a somewhat neglected area because for a long time, people just assumed that you can't do anything about aging. It's a law of nature. Now we're starting to understand the science behind aging, and actually it can be modified. Actually, there are ways of doing it." So, anti-aging is sort of establishing itself within EA, but I would say at this point, it's not a mainstream EA cause area. And later in this talk, I'll go through a couple of reasons why I think it hasn't yet made it into the, quote unquote, mainstream EA discussions yet. So what is anti-aging, and is it possible to extend healthy lifespan? Well, let's start off by looking in nature, because I think a lot of us have this preconception that aging is inevitable. But actually, even if we compare ourselves as human beings to other species, we're really not doing that well. So for example, you may have heard of this immortal jellyfish that can basically live forever because it can revert its cells to a more youthful state. So, it can kind of like turn back the sort of clock on its cells, and theoretically it can live forever. Okay, obviously with our biology as mammals, we can't do this, but it's kind of proof of concept that basically organisms on Earth that have cells just like us, they can live much longer than we currently live as humans. Okay, even within vertebrates, Greenland sharks can live up to 400 years old. So they're the longest living vertebrate, which is approximately 5 times longer than the average human lives. So we're really not that special in terms of lifespan, and there's a lot of low-hanging fruit, it seems to suggest, in terms of modifications we can make to our biology to extend our healthy lifespan. Another interesting example is the naked mole rat. So this creature lives underground, and it lives about 10 times longer than normal rats. But the most fascinating thing about the naked mole rat is that its risk of dying doesn't increase with age. So remember, I showed you that graph where with humans, our risk of dying doubles every 8 years. So that graph is shown here in blue. This is kind of our age on the x-axis, and on the y-axis is our mortality hazard. And you can see that a lot of species, so mice, humans, horses, we have this exponentially increasing risk of mortality. But the naked mole rat, curiously enough, actually doesn't experience this pattern of mortality. It actually has a flat mortality curve. So in a way, it doesn't age in the conventional sense, because although it inevitably sort of dies of predation or of starvation or whatever, it doesn't have this exponentially increasing risk of death. Okay, so with anti-aging, we're basically trying to be more like the naked mole rat and not have this exponentially increasing risk of death. And the naked mole rat has several sort of protection mechanisms against cancer and so on, which you can read about, that allow it to have this kind of flat mortality curve. So with anti-aging, we're thinking about how do we as humans, how do we look at some of these species in the animal kingdom? How can we implement some of their cancer defense mechanisms and their kind of cellular resilience mechanisms to extend our own healthy lifespans and expand our own fitness? So, there's a million different anti-aging approaches I could talk about, but I want to focus on one that's really captured the attention of a lot of people, and I think for good reason. It's these drugs called senolytics. Now, if you haven't heard of them, I guarantee in 5 to 10 years, all of you will know all about them, especially if and when they become FDA approved, which I believe will probably happen in the next 5 to 10 years. Basically, what these drugs do is they kill senescent cells. So senescent cells are these death-resistant inflammatory cells, one of the hallmarks of aging, those 9 underlying sort of features of the aging process. And although in younger life they have some beneficial effects, as they accrue and in older age, they start causing a lot of problems. So they've been linked to multiple age-related diseases such as cancer, Alzheimer's. They release a lot of inflammatory factors, which again, predisposes to a lot of these age-related features of decline. And the most interesting thing is that if we kill off these senescent cells, these zombified cells, we can extend the healthy lifespan of mice quite substantially. Okay, so these are 2 mice who have the same age, same genetics, same diet, same lifestyle, but only this one has received this senolytic therapy. So this is a research from the Mayo Clinic from 2016. So it's just in the last 5 years. And what they've shown is that basically they have a 30% healthy lifespan extension. They have reduced rates of age-related decline, even on some of their behavioral tests, reduced anxiety, based on these sort of behavioral tests. But basically they're less frail, they're in better physical condition, and they live longer. Okay, so this is why a lot of media attention and a lot of scientific interest has been placed on this field of senolytics. And especially in the last 2 or 3 years in biomedical research, a lot of researchers and labs are focusing on senescent cells as a potential therapeutic intervention. Because again, these hallmarks of aging, such as the accumulation of senescent cells, they're linked with all these diseases, right? It's just a matter of time. If you're 60 years old, you're going to have a lot more senescent cells than when you're 30 years old. This makes you a lot more vulnerable to these age-related diseases. So the idea would be to have this hit and run approach, as it's called in the literature, whereby you take a senolytic drug, you kill your senescent cells, and then you do that every few months. And that way you can keep your senescent cell burden down and extend your healthy lifespan. But again, this isn't a panacea. Senolytics aren't going to allow people to live 1,000 years old, but they might add a few years. And in combination with other therapies, the benefits to a healthy lifespan could be quite substantial. So I just want to really emphasize this key point, which is that when we talk about anti-aging and lifespan extension, we are not talking about making people older for longer. It's not about keeping a 90-year-old alive for an extra 2 decades. To believe so is actually, it's got a term, it's called the Tithonus error, based on this Greek mythology. So the Tithonus error is the incorrect belief that extending life means making people older for longer. And actually, the beautiful thing about anti-aging is that several strands of evidence suggest that when we target the aging process, we're actually extending the healthy rather than the unhealthy period of the lifespan. One strand of evidence is from centenarians. So these are people who live over 100 years old. They tend to be more resilient to age-related diseases and spend a greater proportion of their lifespan free from these age-related diseases than the average population. Another strand of evidence, as we looked at, is that when you treat mice with these anti-aging compounds, they don't simply remain frail but alive for longer. It's actually the case that they're healthy and their healthy lifespan is extended, okay? Another way to phrase this is compressing morbidity. So typically at the end of life, the average human being will have 10 to 15 years of chronic illness where they're really going downhill. But actually the centenarians and in the mice, when we use these anti-aging therapies, or just for people who have these genetic predispositions to live longer, they actually have a longer period of healthy life, and then before that kind of decline. So one interesting kind of thing to consider is that there is a little difference between anti-aging interventions and conventional medical interventions, okay? Actually, the difference is that when we think about anti-aging, as we talked about, we're intervening while the person is healthy. So you take an average 20 or 30-year-old and you start them on the anti-aging sort of series of therapies to keep them biologically young, right? We don't wait until someone gets to 80 or 90 and they have all this degeneration in their body and then intervene, because at that point, the ship sailed, they're on that downhill sort of trajectory. Whereas that latter case is actually exactly what current medicine does. We basically wait until someone has a clinical pathology, like they're diagnosed with cancer or with heart disease, and then we try and intervene. But the problem with that approach, as we know from the low success rates with a lot of cancers and with Alzheimer's, basically there's not a lot you can do in a lot of cases, is because we've just tried to intervene too late in this situation. Really what we need to do is prevent people from accumulating the biological damage, i.e. the aging that leads to these conditions. It's not to say that we can never cure cancer. It's not to say that we shouldn't try. It's just to say that we should try and look towards intervening earlier upstream of these kind of diseases of old age to extend the healthy period of life before these diseases become so much more prevalent. So another way to phrase this is the goal is to delay, slow, or prevent age-related diseases such as cancer, diabetes, heart disease, and Alzheimer's. So a question you may have is, why should we not just try and cure the individual diseases? Now, obviously, this is what a lot of the biomedical funding is focused on. Cancer research, Alzheimer's research, et cetera, is absolutely through the roof. But there is a huge advantage of slowing the aging process compared to trying to treat these individual diseases. And this is called Tauber's paradox, right? So basically, if you were to cure cancer tomorrow, all forms of cancer, research has shown that it would only extend healthy lifespan by about 3 years, okay? And that's because if we go back and remember that exponential increase, exponential graph with all the age-related diseases, if you take out cancer, it just means, sure, you might live a few years longer, only to have heart disease or diabetes or another age-related disease. So in a way, because with aging comes so many different ways that the human body can fail, cancer being one of them, Alzheimer's, neurodegeneration, like there are so many different ways the body can fail. If you're not treating the underlying root cause of aging, if you're just treating an individual disease, the bang for buck is going to be a lot less. Whereas if you're kind of targeting aging, you're slowing that degenerative process, there's much more value to be reaped in terms of extending the lifespan by targeting the root cause rather than the quote unquote symptoms of aging, which are the diseases of aging. Some people in the field have called, this healthcare as opposed to sick care, i.e. traditional medicine, because we're keeping people healthy rather than waiting until they get sick and then trying to do something. And this, again, just illustrates this point that typically a person will increase in their performance and so on until about 30, and then they'll have this steady decline due to the aging process, and then death. Now, if they use some preventative approaches such as eating a healthy diet and so on, they may make it a little bit further down the longevity sort of spectrum. But really what we want to do ideally is use interventions to maintain people at that peak state of performance and health, possibly for several extra decades or so on. And that's what anti-aging is about. It's about keeping people at their optimal state of biological fitness. That could be a biological age of 20 or 30 years, and keeping people at that state for as long as we can, so they don't go down this this status quo kind of pathway of just degenerating and then ultimately dying of one of these age-related diseases. So just to give you a little idea, Lifespan.io is one kind of advocacy platform and charity in this space. And I just want to draw your attention to the connection between donating to geroscience, anti-aging sort of science, and actual progress in the field. So they've had a lot of sort of collaboration with different labs, and these are just some of their campaigns where they raise 20, 30,000, 70,000, and they actually put that money towards researching some key sort of areas in this field that can help to move the needle. Okay, and this will be important later on when I talk about the funding and how this links to EA principles of having bang for buck and having impact. But just know that there are these initiatives in which people know that if we can understand the biology of aging, we can develop these therapeutics. So it makes sense to try and finance and fund some of this aging biology research. All right, so let's dive into anti-aging now. So we looked at this, and again, it's about slowing aging rather than treating the individual diseases of aging. Sorry, I think I got my titles a bit mixed up there. But if we think about what anti-aging is, there's actually many different approaches. We talked about senescent cell clearance, which extends the lifespan up to 30%. But even drugs like metformin, which is this common type 2 diabetes drug, has been shown to extend lifespan by 5% and is actually currently being tested in a large clinical trial known as TAME, targeting aging with metformin, which is a $75 million trial over 6 years that commenced last year, which will be the first ever anti-aging sort of large phase 3 trial. But even rapamycin, which is also being tested in a large clinical trial in the US, this is a drug that's FDA approved for kind of organ transplants and coronary artery stents. This drug extends lifespan 20% in mice. And, again, some people read this literature, and there are people today who are taking rapamycin based on the evidence, because in fact, in one paper, there's an interesting paper in which the author suggests that not taking rapamycin could be as bad for your health as smoking in terms of your relative risk, because of the life extension benefits of rapamycin. So there's definitely a lot of options, and there's a lot of possibility for life extension. I mean, yes, these are in mice. Will they translate in humans? The answer is, at this stage, we don't know. However, given a lot of different strands of evidence in terms of human genetics of centenarians, coupled with the mice studies, coupled with biomarker studies, there is a pretty high likelihood, observed by most people in the field, that something will work, because there are over 100 different therapeutic approaches that extend lifespan in mice. Very likely some of them will work in humans, but it's a question of how long do we take to gather that that data. And again, it comes back to how much funding does the field receive. So rapamycin, as I mentioned, it's being studied. Rapamune is kind of or sirolimus, kind of the brand name. And the Pearl study, participatory evaluation of aging with rapamycin for human longevity. This is this sort of, I think it's about $600,000 clinical trial that's being run in the US by Ageless Research, which is kind of an anti-aging drug supplier, to see whether this drug actually extends the healthy lifespan of, or whether it kind of delays the onset of age-related diseases, which is kind of a proxy for slowing the aging process in humans. And in mice, it extends lifespan, as you can see by these survival curves here. And metformin we talked about. Common diabetes drug. It's being tested by AFAR, the American Federation of Aging Research. And this is Nur Barzilai, who's a prominent researcher in this field, who studied the genetics of centenarians quite extensively. And again, the idea behind this trial is to convince the FDA to consider aging as a disease indication, as we would do with diabetes or heart disease, and metformin as an intervention. Now, this is quite a, if you think about it, this is quite a paradigmatic shift, because in medicine today, aging is not a disease, okay? Because actually, to take the strict definition, anything that more than 50% of the population has can't be considered, like a disease, okay? So, but given that aging is this huge risk factor for all these different diseases and conditions, the idea is, well, maybe we should consider aging as a disease, and then some of these therapies like rapamycin or metformin can be thought of as treatments for this disease. Yes, everyone ages, but as we saw, it has this exponentially increasing risk of all these diseases, so it's something we may as well treat. So this is the ambition of, Nur Barzilai and the coordinators of this clinical trial. So let's just quickly zoom into longevity biotech and discuss where the field's currently at. Now, the reason why we consider the field neglected is because although globally there's a lot of money in biomedical research per se, most of that money is looking at targeting the diseases of aging rather than the root cause, targeting the hallmarks of aging, extending healthy lifespan, okay? So to give you an idea, the largest sort of funder of biomedical research in the world is the NIH in the US, which is the National Institutes of Health. So they have an annual budget that sits around 45 billion. And you would think that given everything I've presented to you in terms of the evidence regarding aging, regarding its connection with disease of aging, and the immense sort of healthcare costs associated with those diseases, you would think that it would make sense to really spend a lot on trying to treat aging because it's such a huge problem. But unfortunately today, that's not what we see. So globally, there's about $100 to $200 million in sort of geroscience trying to treat the root cause of aging. So it's less than 0.2% of the NIH's budget. So although aging research, the NIA, National Institutes on Aging, has a budget that's in the billions, and it's about 7% of the NIH's budget. Most of that quote unquote aging budget isn't trying to solve aging. So it'll be looking at studying, okay, what are the psychiatric conditions people have in older age, or how do we define aging? Do we call, like, sociological research, do we call people elderly or wizened or whatever? But only a small fraction is actually trying to treat the problem at its root cause by looking at the underlying biology, the biochemistry, the cell biology, and trying to intervene to treat the root cause and subsequently extend the healthy lifespan. Another issue is that you've got this kind of, it's been called the triangular logjam of aging research, which is this kind of logjam or paradox where the government funds science that is popular amongst people. Science that is popular, such as cancer research or Alzheimer's research, receives more funding, and remains popular. And because it's popular and it's receiving a lot of funding, the public support that science that is popular. So you have this kind of self-perpetuating cycle where these big fields like cancer research and heart disease research, they've got so much momentum because there are so many labs working on them. So they get a lot of publications. So the government invests more money, and the public really cares about this sort of research. And you have this sort of triangular sort of feedback loop. And that's not to say that there's anything wrong with trying to treat those conditions per se, but as we looked at in terms of bang for buck, we really need to invest more in terms of trying to understand the aging process, which is basically the precursor to all these diseases. Yes, it might be 1, 2, 3 decades before the onset of the clinical symptoms, but in general, treating things at the root cause is a wise approach. And in this case, in biology and in medicine, a lot of the evidence suggests that it's no different. So fortunately, the field is rapidly advancing in the sense that the work that has been performed in the laboratories is being spun out into biotech companies. And this is leading to large grants that are going towards kind of putting these sort of technologies through their paces, running clinical trials, and so on. And so here's just a small sample of the 150 longevity biotech companies that are currently in operation. So one of the biggest ones that is interesting because it has quite a large budget, but you've probably never heard of it, or maybe you have, is called Calico. So Calico is actually run by Google. The founders of Google started this company. It's backed by Google. It has a budget of around $2 to $3 billion. But unfortunately, despite its huge sort of resources, it hasn't actually produced a lot of really impactful results. Calico Labs, they haven't produced a lot of impactful results, and this is why some of these smaller operations that have basically like very targeted research looking at specific hallmarks and so on are actually potentially pushing the needle forward even further, which is why like Lifespan or SRF, Sensory Research Foundation, why these organizations have historically been kind of better bang for buck in terms of pushing the needle, moving the needle. So as I wrote here, the main bottleneck is in the basic science research. Yes, these companies have huge budgets, but what are they primarily focused on? It's taking existing technologies from academia and building companies around them. But that part, doesn't, that's not really a bottleneck, because a lot of VCs are kind of seeing a lot of interest, or they're recognizing interest in these technologies globally. And so the main bottleneck is in the actual science. How do we make more discoveries in this area that will lead to new therapeutics? And that's why in this talk, I'm not arguing that we should finance these sort of these companies as like VCs. I'm suggesting there should be more charitable investment in the basic science of aging, i.e. geroscience. So again, there's no shortage of compounds that extend lifespan in mice. So if aging research had a 10x or 100x budget, we could test all these drugs at a much faster rate. Okay. If you go to Laura Deming's website, she's a longevity biotech venture capitalist. She runs the Longevity Fund. You can read about all the different approaches that extend lifespan in mice. And if we had more money in this field, we could be testing all of these compounds. We could actually be seeing, do these compounds, do they actually work in multiple sort of mouse models? Do they influence human biomarkers? And we could really be studying them, because in all likelihood, some of them probably will extend lifespan in humans, but until we actually run the experiments, it's not easy for us to know. All right, so onto one of the last sections, which is evaluating aging research. So should we donate? What's the cost benefit analysis, or like, what is the return on investment in terms of qualities and in terms of, basically capturing value if we donate to help support aging research, i.e. geroscience. So I want to kind of direct your attention to this really good post on the EA forum by my colleague Emmanuel Ascani. So basically, there are different ways to model the effect of donating to aging research. And I'm not saying this is necessarily the best model, but it is one of the few models or few attempts at a model. Basically, he starts off with this premise that at some point in time, it's likely that we'll hit this point called LEV, which stands for longevity escape velocity. Now, basically, that means we reach a point in time after which we have therapies that extend your lifespan, maybe 10 years. But in those 10 years, there's even more R&D that creates better therapies that allow you to get an extra 10 years, and so on and so on. So you kind of escape the aging process, okay? So even if the first generation of technologies don't give you the ability to totally transcend aging, you have this kind of ripple effect, if you like, or each technology builds upon each other, so that if you have access to the first generation, it'll give you enough lifespan extension to benefit from the second generation and so on. So basically, after this point, no one dies of aging. Okay, that's sort of what LEV means. And if you think that donating a certain amount of money can bring LEV forward by 1 year, then all you have to do to kind of approximate the value that that is associated with is just multiply the population who would have died that year, okay? And remember, it's currently around, 35, 40 million, okay? Multiplied by the expected healthy lifespan after LEV is reached, okay? So to give you an idea, the population who would have died, if it's similar to today's levels, that's about, 40 million, or we'll say 36 million. And lifespan after LEV, as we touched on earlier, taking a conservative estimate is about 1,000 years. Okay, so if we multiply 1,000 QALYs, 1,000 years of healthy lifespan, by the number of people who would have died in that year, but because we've kind of brought LEV forward, no longer die, that's 36 billion QALYs, right? So then all you have to do is make an estimate. And obviously this is really not easy. And this is why I think more research needs to go into these sort of estimates. But as SENS Research Foundation have calculated, they think that $50 million in aging research can bring LEV forward by 1 year. So you pay $50 million, you bring LEV forward 1 year, and at some point in the future, even if it actually doesn't matter what the timelines are, even if it's in 1,000 years or so on, as long as the population sort of death rates, are, kind of on the same order of magnitude, and the lifespans are on this sort of order of magnitude, it's absolutely immense bang for buck in terms of the amount of money you're investing for how many QALYs, quality adjusted life years, you are saving, okay? And it dwarfs, even the Against Malaria Foundation, all the top GiveWell recommended charities. Okay, so you can read about, if you want to go through, I've given a very simplified version of the model. If you want to read all the mathematics involved, you can read this post, which is called A General Framework for Evaluating Aging Research Part 1, Reasoning with Longevity Escape Velocity, which is on the Less Wrong forum. So yeah, basically, as you can see, it's much better bang for buck in terms of the amount of money needed to kind of bring LEV forward and how much value we get from that in terms of QALYs versus trying to save QALYs in the current ways. So if you're a curious-minded person, you may have thought of a few potential repercussions of extending a healthy human lifespan, as most of us naturally will think about. So let's just go through some of these. So the first and most obvious one that probably comes to mind is, will the Earth get overpopulated if everyone's living so much longer, and if birth rates remain as they are currently, then won't we have this population explosion? So I'll just go through a few points on this. First point is that global population currently is not, a lot of people have this idea that we're on this exponentially increasing population curve, but we're actually not, because of kind of the demographic transition model and the idea that birth rates are falling quite substantially in a lot of developed countries, and they're kind of plateauing in a lot of the up and coming parts of the world, such as Southeast Asia and Africa. So basically, population is predicted currently to peak at around 9.7 to 10 billion and then go into decline by 2070 due to falling birth rates. So the current status quo is that population is going to rise, and then this is why Elon Musk has tweeted about underpopulation being a bigger problem than overpopulation, because at this point, there's actually, this has already begun in some parts of the world, like Japan and Italy, because they have these aging populations and their birth rates are below replacement level. They have this sort of declining population curve, and on a global scale, that's currently predicted based on demographic, models to occur after 2070. So you have this kind of peak. It's kind of like a parabola shape, I guess. It kind of goes up and it goes down. Another piece of evidence to keep in mind is that analysis based on populations in Sweden has suggested that extending lifespans has only a modest effect on population size. So here's the graph from the original paper, and you can read the paper here. So it's a paper from 2020. They've basically shown that, the paper's from 2010. They've shown that if we were to completely halt aging after the age of 60, it would only result in a 22% increase in population size after 100 years. So yes, the population would increase, but I think a lot of people overestimate how much the population will increase. Now, obviously, there are a lot of issues to consider because, our consumption today of a lot of resources, including CO2 emissions, is unsustainable. That's a fact. But the thing is that we don't need a lot of people to die of aging in order to reduce emissions, in the same way that we don't need people to die of COVID to reduce emissions, right? Anyone who suggested that we should allow people to die of COVID to reduce our emissions, obviously, that would be quite an unpopular opinion. And really, if we follow the logic, it should be the same with aging, because if we have technology to allow people to live healthier for longer, although we definitely need to tackle climate change, that should come through technological interventions, not through basically letting people die of cancer, heart disease, and so on. So basically, if we really think it through, there's not really a case to be made that overpopulation justifies halting biomedical research into anti-aging. Now, in the long-term future, okay, let's say we completely halt aging and no one's dying of aging, and lifespans are in the thousands and birth rates are positive, then yes, the population at that point will continue to grow. But the point at which technology can no longer basically balance or kind of deal with the rapidly expanding population is so far down the track that it's not really that relevant to today's discussion, when there's such you could call it a huge humanitarian crisis in terms of the number of people dying of aging. And there's many potential long-term solutions, such as becoming interplanetary or simply having a choice. Do you want to use anti-aging technologies or have children? So there are definitely solutions to those sorts of problems. Another common critique that anti-aging often gets is, won't this technology only be available for the Jeff Bezoses of the world, the rich, and they'll have these long sort of lives, almost dystopian novel kind of depiction, while the rest of us live in squalor and die of cancer and so on. Well, fortunately, there's a lot of safeguards against this situation, and even if it happens, it's really no different from a lot of technologies that we currently benefit from. So the first thing I'll say is, a lot of medical researchers are really focused on the equity aspect of this, and a lot of these biotech companies, they definitely have, not only from just a kind of economics perspective, given the huge market size, they have an incentive to lower the cost, but also from like a value and mission side of things. A lot of them have it in their kind of mission to ensure equity, ensure the technologies are equitable. But also a lot of the aging researchers have established the Academy for Health and Lifespan Research, which has in its mission to make the technologies available to all. So there's a lot of push in the field to ensure equity. The other thing is that the price of many revolutionary technologies decline over time. So if we think about sequencing of the human genome, which I've got a graph for here, the first genome was in the millions, it was 100 million, and now you can do it for a couple $100. A lot of these sort of biomedical technologies do rapidly decline in price, even if we think about smartphones and a lot of other technologies. Another point is that generic forms of medicines are likely to become available once patents expire. Some of the most life-saving medicines today, such as metformin for diabetics and all these sorts of drugs, they were once very expensive, but the cost has dramatically dropped by hundreds of fold. And with longevity technologies, we'd kind of expect to see that same kind of pattern. Another point is that many technologies that were once only for the rich are now available to the masses. So most of us have access to commercial flight and cars. Well, if we go back before these were widely available, someone could have made the argument, well, I don't think we should develop automobiles because they might only be available for the rich. It would be kind of a silly thing to say with hindsight, because now, obviously, although they were initially available to the wealthy, now kind of everyone has access, or most people have access to these forms of transport. And so the fact that they were once only for the rich doesn't seem to be like a strong argument supporting the idea that they shouldn't have been developed. The technology for cars and commercial flights shouldn't have been developed. So yeah, even if the rich were to have access first, it's not ethical to withhold the technology from society, because if you think about the top cancer therapeutics today, a lot of us would not be able to afford them. If you have the funding, you might be able to buy these expensive therapies, especially in the US. I'm talking about where the prices are astronomical for certain therapies. I mean, that's already the case today, but are people coming out and saying, oh, we shouldn't research cancer because we might develop drugs that only the rich can afford? Of course not. We recognize that there are these problems, and we have to basically allow biotech to kind of create these new therapies with the vision that the price will come down naturally. So yeah, overall, again, it's not really a strong argument against this technology, the fact that the wealthy might have first access. So another common point that comes up, this is more of a sort of philosophical point, is, what is life about? Would life lose its meaning if we have these kind of infinite horizons or much longer lifespans? Well, this may seem like sort of a compelling argument on the face of it, but when we dig down, it's a bit of a silly argument because people are entitled to create their own meaning in life. No one can say, oh, I think your life is not meaningful enough, so I'm going to shorten your life to make it more meaningful by letting you die of cancer. Really, the individual should have the right to live longer and live as long as they perceive as meaningful. Older individuals today, they find all kinds of ways to find meaning in their life, from finding new hobbies to new careers. People are transitioning to new careers later and later in life, spending time with their families and so on. And so that's led to some people to say, life gives meaning to life. We don't need to have this fixed end at 80 years, 90 years in order to have meaning. Why can't we just enjoy ourselves? And a key thing to remember is we're not talking about frail people who have these age-related comorbidities, because that is the specific aspect of biology that we're treating. So if you were 80 years old chronologically, but you had the biology of a 20 and 30-year-old, and you could run marathons and you could do everything that you wanted to, then why wouldn't you want to keep living? So really, again, this isn't a major threat to investing in longevity science. Another common argument is if we have these life extension technologies, could potential kind of dictators remain in power for a lot longer? And some empirical research has been done on this topic, and Anders Sandberg from the Future of Humanity Institute has written some papers about this and shown that very few dictatorships end as a result of natural death, and slowing aging would have minimal impact on the kind of length of the reign of these dictators. And part of this is because family bloodlines often allow a kind of functional immortality in the absence of a biological immortality. So fortunately, the evidence doesn't seem to suggest that we would have these longer dictatorships if we were to abolish the aging process. Another common question, which I guess we've touched on, is would we spend more time in ill health? But as we've talked about with the Tithonus era, actually the goal of anti-aging is to extend the healthy period of lifespan, not just lifespan per se. In fact, you could argue that it's quite morally abhorrent to extend the unhealthy period of lifespan. Like if anti-aging technology were just to allow, say, a 90-year-old who's frail and sick to live an extra 10 years in that state, you could actually say that that's morally questionable or quite unfavorable. But that's fortunately not what we see empirically when we think about anti-aging, and what we've seen in, again, the centenarian research and mice studies. We see that the healthy period of lifespan is extended rather than the unhealthy period of lifespan. And now this is a concern that EAs tend to have with regards to adverse social effects. So dictatorships we've talked about, but some EAs are concerned that the rate of technological societal progress may stagnate if we weren't to have the same kind of generational replacement, or if we weren't to have sort of leaders die of aging. There's this idea that science advances one funeral at a time. And actually, from recently, there was a paper this year that actually does support that idea to some extent, that when a prominent scientist dies, it actually creates a bit of a vacuum in which other ideas and new paradigms can be introduced. However, we've got to balance that against benefits of anti-aging, such as increased cognition spans, because if we have the best scientists in the world not undergoing that kind of cognitive decline that we see with aging, especially when someone's 70, 80, 90, they're not going to be as sharp as they were previously because of the natural sort of neurodegenerative process that occurs with aging. But once we have anti-aging, and you can have 80-year-olds who are just as wise as they are, given their chronological age, but have the mental acuity and focus of, say, a 20 or 30-year-old, then you could start seeing a lot more advancements and benefits. That said, there are also arguments you can read about on the EA forum and so on about the idea that slower progress could actually be a good thing in terms of technology, because by having slower progress, we have more time to mitigate existential risks such as AI safety and so on. And there's a line of argumentation there as well. So finally, how can EA help? So there are many ways to support anti-aging. There is donating to fund the research, as we've discussed. But even if you have the proclivity for it, working in longevity biotech, you can look at this great website curated by a friend of mine, Nathan Cheng, called longevitylist.com, that has an up-to-date sort of list of all the different roles in different longevity biotech companies. You can invest in longevity biotech companies, and there's a good up-to-date list at longevitymarketcap.com. You can contribute as a content writer to the wiki that we're building, which is longevitywiki.com. You can encourage EAs to consider anti-aging as an important cause area, because as we said, it's just kind of burgeoning as a cause area, and it's not, it's not the most well-established cause area in the EA circles just yet. Or you can kind of write posts on the EA forum or less wrong about anti-aging. There's definitely an appetite for this content, and if you fancy yourself a good writer and a good researcher, there's a lot of opportunity to contribute in this capacity as well. So just to recap, in terms of the value at stake, there's a great economic analysis from this year by David Sinclair and some colleagues at University of Oxford, in which they calculate that extending healthy lifespan by 1 year is worth $38 trillion based on the value of statistical life model. And as we talked about, there's billions of QALYs to be recuperated or captured should we be able to, basically extend lifespan by 1 year, or even if we bring LEV forward. So I think the key thing to remember with anti-aging is that there's a lot of value at stake, and it's potentially very cost effective. Now, this second last slide is just saying, why has EA not focused on anti-aging given everything I've gone through in this talk? And here are a few reasons that a few EAs who kind of toe the line between EAs and longevity enthusiasts have come up with. I think one point is that I don't think there's a lot of widespread understanding of scientific feasibility amongst EAs, because a lot of EAs come from philosophical, well, there's a wide variety of backgrounds, there's computer scientists, there's philosophers, there's all kinds of backgrounds, but in general, there doesn't seem to be a huge concentration of kind of biomedical into EAs essentially. So I think the lack of feasibility is one aspect. Another aspect that's really, I think, really substantial is the fact that not many people have tried to calculate the actual value, of slowing aging in terms of how much money you need to invest to recuperate how many quality adjusted life years. Even Open Philanthropy Project, they did what they described as kind of a medium depth investigation into this field, but they didn't actually attempt to do any calculations. And so I really, like, a few of us in the field really think this is kind of an error, because they haven't actually tried to, evaluate, is it cost effective or not, which ultimately is the key question when we're talking about EA and bang for buck. Also concern over social repercussions, such as the effect on the long-term future, as we've touched on briefly. And I think another aspect is the fact that anti-aging doesn't neatly fit into the large categories, the broad categories of short-termist cause areas, which are helping people who are alive right now, and long-termist cause areas, which are, helping the millions or billions of people in the future, because it's kind of medium term. We need to invest a bit of research now, but it could be, 10 years, 20 years, 50 years. So it's kind of this medium term that kind of doesn't fit nicely into the category. So that's why we think, EAs, again, why they may not have been exposed to this area. And just to illustrate this point with some evidence, this is a poll of EAs recently. I think it was 1 or 2 years ago. And you can see that in terms of top EA cause areas, long-term future, most EAs identified as their top cause area. Global poverty was second. And then you have some others. But obviously, anti-aging isn't there yet, potentially for some of the reasons that I just described. So again, if we look at scale, neglectedness, and tractability, the main EA kind of tenets or criteria for charity evaluation. Well, the scale of anti-aging is immense. It's all humans alive today and in the future. Neglectedness, we looked at less than 0.3% of medical research budget globally. Tractability, we looked at evidence from the past 5 years has demonstrated life extension in mammals and biological age reversal in humans. And cost effectiveness, potentially enormous based on the preliminary models, although future models could, sort of verify this dollars per quali bang for buck. So to summarize, aging is the leading cause of death and suffering in DALYs amongst humans worldwide. So there's a tremendous amount of value at stake. Scientific evidence supports the feasibility of life extension technology, and investments into anti-aging science may be one of the most cost-effective means of doing good. So thanks everyone. And if any of you would like to follow up, after the Q&A and so on, feel free to email me here.
All right. Thank you, Jack, for the great presentation. It was really very thorough and very educational. We'll now get into a Q&A. So please ask any questions you have in the chat or on the Google form. If you prefer, just put the form again in the chat there. To start us off, I know you already touched on this a bit, but what are your thoughts on potential ethical issues in anti-aging treatments rollouts in terms of disparities between the developing world and the developed world? I mean, we can kind of already see this in our current COVID vaccine rollout. Some countries are missing out. And then, is this a major issue, or will this be fixed?
Yeah, I mean, ideally, if we can develop anti-aging technologies and have them accessible to everyone in the world on the same day, that would be the ideal situation. The way the world works, that's never really the case with any, new impactful technologies. So, there is a likely chance that there might be somewhat of a lag between when, the early adopters have access to this technology and when, the next wave have access and so on. But really, that's no different from any biomedical technology. Like the best cancer therapies available today, you won't find people in, sub-Saharan Africa in a lot of cases, depending on where they're living, having access to those technologies. But does that mean that those technologies shouldn't have been developed? Should we not have put the money into developing those cancer therapies? Well, it's kind of hard to make that argument, given that they are saving, millions of lives in some respect. Obviously, potentially not providing the life extension that that longevity biotech may provide, but I think it's hard to make the argument that we should halt all biomedical research into a field that could extend potentially, all of our lifespans, depending on when we have access, just based on the temporary period of inequality. I mean, imagine making this argument with something like a smartphone or an automobile. When the first cars came out, oh, we shouldn't develop this technology to make a car because for a small period in history, only some people have access and some won't. Well, yes, that was the case for a period in time. Only the rich could afford automobiles when they were first developed. But now, the market size is so huge and pretty much, most adults do own a car. And so, it's kind of the same with longevity technology. Yes, it's possible that there may be this initial period in which there's that inequality, but ultimately that's no different from any technologies that are also transformative. I mean, having a car versus, back in the day, having, a horse-drawn cart or a bicycle or something is going to really have a big impact on your life. And so, there was that period of inequality, and that was deemed acceptable, and really there's no difference with anti-aging technologies.
All right, yeah. S asked earlier, how are senolytics selective for senescent cells? I think I was just back on the...
Yeah, so that's a great question, digging into the biology. So there's actually a number of different sort of senolytic approaches. So some of them involve kind of activating the immune system to selectively target senescent cells. Some involve directly removing the cells. Some are even some new xenotherapeutic approaches involve basically reprogramming the cell to basically change its phenotype away from the SASP, which stands for senescence associated secretory phenotype. So basically loses its senescent features. So there's if you follow up with me on email, I can link you to some really, really good papers that summarize the multiple different xenotherapeutic, senolytic strategies. But yeah, the field's really exploding. So there's no one single way. I mean, some involve, like I said, killing the cells, reprogramming the cells, augmenting the immune system to kill the cells. So yeah, there are a lot of different approaches being developed. It's a very exciting space.
Yeah, definitely. We have another question. Wouldn't it be more efficient to do political lobbying for more public funding than to donate directly for research, given the enormous size of public funding for health research in general?
Yeah, absolutely. I mean, I think that is definitely something that would be beneficial. But again, it goes back to the triangular logjam of aging research. So because you have these large institutions, these large cancer centers, these dedicated centers to age-related diseases, it's not as simple as talking to your local MP and having millions redirected away from those major sort of centers, right? It's there's a lot of kind of careers and involved, and a lot of momentum behind the existing paradigms of treating the individual diseases that it's challenging. But that said, I think there is value to it. In terms of just more direct ways of impact, if we directly finance the research in these kind of crowdsourced ways that Lifespan is doing, that SRF are doing, it just bypasses all that bureaucracy, and it just allows us to just pinpoint the key experiments that are needed to move the needle in the field and really target those. But definitely, I mean, advocacy is so crucial, and that's why we, like the project that I'm involved with, the Longevity Wiki, is designed for that very purpose. We're building a platform for the purpose of advocacy. And the goal would be, as more and more people get educated in this field, this will eventually lead to more of the public, more public appetite for this kind of research, and hence more government funding in response to that. Because the problem at the moment is that no politicians are going to win votes for funding geroscience research, because no one even knows what geroscience means. So this is why there needs to be like kind of a progression from society getting on board with the idea of targeting aging, understanding the connection between aging and the diseases that kill most of us, and then recognizing that we need to intervene, and therefore lobbying the government. But at this stage, there's just not enough societal awareness of the kind of link for it to be effective, I would envision. But yeah, I definitely think that in the longer term, getting more government funding in this area is really, really crucial, for sure.
Yeah. Continuing the theme of anti-aging knowledge, when did serious exploration into directly solving the problem of aging begin? And when
That's
did...
a great,
yeah.
Yeah, that's a great question. So actually, there were a couple of pioneers sort of in the early 2000s who kind of proposed this, geroscience hypothesis of kind of treating the aging process. But really, it's only been in the last 5 or 10 years that the empirical evidence has actually validated a lot of the initial kind of theorizing of these individuals in the early 2000s, especially in the last 5 years since senolytics, because these are, some of the first generations of drugs that you just give them to any kind of, any mouse, and they'll extend their healthy lifespan very consistently. So the field began in the 2000s. I mean, it depends how you define. I mean, people have been thinking about aging for millennia, but in terms of using biotechnologies to directly intervene and slow the aging process, extend healthy lifespan, really in the last 5 to 10 years, the field's just exploded. And it's definitely a field that's really rapidly increasing as more and more people get involved. Even with crypto community, there's a lot of activity there with new funds such as VitaDAO and Richard Hart's large kind of funding of this research, and Vitalik Buterin's donations, who's founder of Ethereum. So there's definitely a lot more activity in this field recently. So I would say that kind of the early kindling of the field was in the early 2000s, and then it's kind of just, it's kind of on quite a steep gradient in terms of the explosion of the field.
Yeah. So in terms of like a timeline, how close are we to applying a lot of these experimental trials to humans? I know you mentioned that Senolytics had trials starting in 2020, but are any of the other ones advancing?
Yeah, that's a good question. I actually have a slide that's related to this question. If anyone's interested, I can email you this deck, and there's another like 20 or 30 slides that cover, just other aspects. And one of the slides is this one from Metaculus, which is Metaculus is a aggregation platform. It's kind of a prediction aggregation platform that takes many people's estimations and kind of aggregates them together using some weighted algorithm. And based on a few hundred people's responses, that Metaculus predicts there's a 59% likelihood that there'll be a culturally significant development in aging research by 2030, which I think is pretty interesting as kind of a ballpark figure of when we might expect some of these advancements to be made. But to answer your question about clinical trials, there's a great website. If you just type in rejuvenation roadmap, you can basically see the progression of all the trials. There's over 50 clinical trials in humans today for anti-aging therapies. So you just type in rejuvenation roadmap, and you can basically track the progression of all those on the Lifespan website. So there's a lot of trials that are either planned or currently in progress that you can just look at. In terms of the big ones, as I mentioned, probably the biggest one is the targeting aging with metformin, which is, I believe, 3,000 patients in the US, like a multi-center phase 3 placebo-controlled kind of trial. And then you've got the Pearl study that we touched on, the rapamycin study. So yeah, none of the big trials have finished yet. They're all kind of like work in progress. So that's why I suggested earlier, probably 5 to 10 years time, we're going to start getting the data. That's when it's likely, as kind of Metaculus seems to predict as well, that we're going to start seeing these like big changes in the field. At this point, it's all very speculative, because those who study the field, generally can have their own predictions of what they may think may come about. But for the lay person, they haven't seen a lot of evidence in humans that it can be done, and hence there's some healthy amount of skepticism. But really, it's in the next 5 to 10 years that we're likely to see some of these big changes.
All right. In terms of building that public knowledge, Alistair asks, what are your thoughts on balancing scientific objectivity and conservatism and hype when communicating anti-aging science to the public?
Yeah, that's a great question. And that's something that with my team at Longevity Wiki, we discuss pretty much every week, because we are trying to maintain a scientifically credible and rigorous approach in how we talk about the science. But we also want to communicate the ideas in a way that makes sense to people. Like if you look at the data, and then you kind of and you kind of recognize the potential applications in humans, then you can kind of see that there is this very real possibility of life extension. And then obviously you do the maths and you see how much impact it could have and so on. And yeah, the impact's quite substantial. So I think it's definitely a balancing act. And I was saying to some of the organizers earlier that I think some of the individuals in the space, like David Sinclair, do a really good job of building hype in the field and interest without actually compromising their scientific credibility. And I think it's testament to this fact that people like Sinclair are able to hold professorships at these quite conservative institutions like Harvard Medical School, whilst also writing a book that's a New York Times bestseller, saying with the subtitle of Why We Age and Why We Don't Have to. So I think there is definitely a way of balancing the hype. And also with some of my colleagues at Longevity Wiki, we also manage the longevity subreddit, which is the largest community. And I think this week or next week, it's going to hit 100,000 people on the longevity subreddit, making it the largest single longevity community. And, when we post on the longevity subreddit and in the moderation process, we're always thinking about, balancing the hype with the real science. So yeah, it's definitely an important consideration.
Definitely. This one comes from pretty early in the talk. Faisal asked, what's the link between the biological age and fitness age, such as VO2 max?
Yeah, that's a good question. And I think, I'm not sure if in this version I have a slide on this. I think I may have a slide on this. Just give me one moment. No, I don't have it in this version. Actually, it kind of links. Yeah, actually, I do have it. So basically, when we think about aging clocks, we talked about the epigenetic clock, which is kind of the first generation of aging clocks. So you basically take a sample of your tissues, you look at the DNA, you look at the methylation levels, and you can tell whether someone is aging faster or slower than their calendar age would predict. But these new third generation aging clocks, they actually do incorporate physiological biomarkers, such as, things like memory, decision, but even as it says here, grip strength, highest audible pitch. So these functional tests, and VO2 max would be one of those functional tests. So basically these new third generation aging clocks, they integrate all these different data points. So like your blood, your inflammation levels, your TNF alpha, CRP, glucose metabolism, adipokines, thyroid hormones, blood lipids, your muscle mass, blood pressure, but also these functional tests such as VO2 max, grip strength, and so on. So actually, yeah, so I would say definitely VO2 max could be one of those functional biomarkers that could be used as part of these third generation multi-omics, combined aging clocks. And I predict, yeah, probably it's likely that it could be used as part of one of these tests.
Yeah. I mean, after hearing all this about anti-aging research, I'm interested to know, is there any programs I can take now to sort of reduce my aging? I've heard of NAD boosters from friends, but any sort of things keep me youthful.
Yeah, I mean, so probably one of the most sound I guess the most sound advice, it really depends on your risk tolerance. So if I was 60 or 70 years old now, I'd probably be inclined to take more risks, maybe try rapamycin. So there's no single approach. It's very personal because it depends on your current health and your current lifestyle. Obviously, there are easy wins. Like if you're eating McDonald's every day, stopping that is probably an easy win. If you never exercise, and starting to exercise is an easy win. Once you've optimized for the basics, like sleep, exercise, diet, then you can start looking at supplements. Like you might look at vitamin D, or the fish oils, or even metformin, or as you mentioned, NAD boosters. But really, a lot of it, because a lot of it they haven't been in clinical trials in humans for a long period of time, like something like the NAD boosters. A lot of the evidence is preliminary. So it depends on how you look at the science and how you read into it. That said, there's obviously a trade-off, but there's obviously an opportunity cost of not taking something, because the status quo is that you're aging. So as long as you think the risks are lower than the opportunity cost, then it's worth taking. But that calculus, until we get a lot more human data, is kind of hard to make. Hence the emphasis of this talk of funding the research, getting the drugs through the trial, so we have data so that we can actually say, oh, NAD plus improves all these biomarkers and it doesn't have any side effects. Until we have these large scale clinical trials to collect that data, it's anyone's guess. And so it really depends on how you look at the literature. But ideally, in the next 5, 10 years, 15 years, we have a lot more trials in this space, a lot more data available. And so we can know, okay, this is safe to take, this is going to benefit me in this way, and so forth. That said, one of my colleagues who's really, really knowledgeable in this space, he's given me his protocol. So if you email me, I can email you with everything that he takes, which is quite an extensive list. So yeah, if anyone's interested, I can send you that.
Yeah. All right. I think that is all for the questions we have tonight. But just before we do wrap things up, if you have any questions on tonight's event, please fill out our form. We greatly appreciate any feedback we get. And yeah, thank you, Jack, for taking the time to present to us. I know I found this relatively neglected field of EA very interesting, and I'm keen to see progress being made in the future. In terms of EA Unimeld events coming up, we also do have a games night this Wednesday if you're looking to meet more people in the community. So yeah, thank you, Jack.
Thanks, guys.
Thanks very much, Jack. It was fascinating.
Thanks, guys. Take care. See you later.